As Mark said, my name is Ifan. I'm a postdoc working with Professor Shuren Song. So today is my great pleasure to be here to share with you some of my research work on using active compliance for robust manipulation. So let me explain what that is. So I work on robotic manipulation, which is basically trying to make robots do useful tasks with their arms and hands. As you may have seen in recent news, there has been a lot of very impressive robotic manipulation demos on YouTube. Those companies make beautiful hardware and have very impressive manipulation skills demonstrated. But when can we see them not only in YouTube, but in our daily life? And when can we have robots actually around us to do the chores that we don't want to do? So somehow there is still a gap here. And in my opinion, the gap is mostly about the robustness of those manipulation skills. Basically, you need the ability to handle all kinds of uncertainties and disturbances that are inevitable in real life. And in my talk today, I'm going to talk about one particular way to improve the robustness of robotic manipulation. This is active compliance. So let me explain what this word means. So compliance is a motor property that describes the relationship between force and motion. So even for the same motion, if you use different compliance profile, it will react to external force very differently. So this is something humans are very good at utilizing. So for example, this is me trying to grab the empty plate. I didn't pay attention to some other plates in my way. So if I do the grabbing with low compliance, which means my hand is very rigid, I literally push away any obstacles. Okay? I can carry out the original desired motion. But if I execute my motion with high compliance, my motion will deform around the obstacle. Okay? Here's another example where I'm just swinging my arms, but there's an obstacle in a way. This time it's a rigid wall. If I do it with low compliance, I'm hurting myself. Okay? I'm going to introduce a lot of contact force. If I do it with high compliance, I can actually engage the contact pretty gently. So as you can see, those different profiles are good for different things, right? Low compliance, or in other words, high stiffness, is good for precise tracking under disturbances. But they can be dangerous when you are engaging unknown contacts. The high compliance control is good for adapting to new constraints, but they are very susceptible to disturbance forces. And the good thing is that for our robot, it's possible to implement any of them. So this is called active compliance. You can implement any compliance profile on a robot using control. Then this brings us with the question, for manipulation, can we design our control to take the best of both worlds? So that's basically the central question I'm trying to answer today. And I'm going to give you answers from two perspectives. First is an analytical perspective, during which I'm trying to explain to you how exactly does compliance help in manipulation, and how can we best utilize the helpful bit. But the analytical way is not always possible. So in the later half of the talk, I will give you a learning perspective where we can obtain a compliance control strategy directly from human demonstrations. Okay, so let's jump to it. Okay, so for the analytical perspective, the central question here is, can we improve the robustness of manipulation? Can we make manipulation to not fail in the face of uncertainties and disturbances, right? So we might as well ask this question, how exactly does manipulation fail? Okay, so let's zoom in to the exact time instinct of the failure of a manipulation task. And actually we can summarize the failures into two failure cases. One is unexpected contact mode. So a contact mode is basically saying, like a contact point could be either sticking or sliding or disengaging. Okay, they're discrete modes. You might be expecting some of them, but for example, in this case, if the contact point with the robot suddenly changes from sticking to sliding, that basically marks the failure of the task. So the second failure case is, we call it kinematic ill conditioning. Let me explain with this example. Here, this robot is attempting to slide the white item upwards, lift it up, but due to some calibration error, its velocity is wrong. Its velocity has a component that is penetrating the wall. So instead, the robot is creating huge internal forces at the contact, which eventually breaks the fingertip. These are the two failure modes. How can we avoid them? I will start from the second one, the kinematic ill conditioning. It turns out this situation happens when you have a constraint violation. For any manipulation problem, there are two sources of constraints. One from the context in the system. The other is basically your control. So if you apply high stiffness, like very rigid control on a robot, you are equivalent, you're basically applying a constraint to the system. And that constraint might not be compatible with what already exists in your environment. So, and at any time instinct, those constraints are linear constraints on the system velocity, which means we're having an infeasible linear system. Okay? Then we can use our knowledge of linear algebra and use the condition number of this linear system to quantify how far away the system is towards being infeasible. With some robotics-related post-processing, we can use it as a metric. We call it the crashing index. This basically describes how badly the system is ill-conditioned. So in this analysis, we can see that how compliance can be helpful here. Basically, compliance can be helpful by giving up some controls. Okay? If there are already constraints in the system, then your robot, well, dear robot, please just let it go. You don't have to have full control of every single degree of freedom. Okay? So this way of selectively apply control in certain direction can be implemented by a certain compliance control method called hybrid force velocity control. This is a traditional method very popular in industry like surface polishing. The idea is very simple. You look at your robot's action space. You can decompose them into two parts. In one of them, you can let the robot be very stiff. You do high stiffness control, which is usually represented by velocity control here. In the other space, you can do soft force control. And apparently, there are many options of selecting the number of dimensionality and the direction of those controls to be. On the one hand, you still want to finish your task, right? You still want to achieve the desired system velocity. On the other hand, you want to minimize the crashing index, so you stay away from getting ill conditioned. And that problem of computing the best hybrid force velocity control can be solved in closed form. So we call it the hybrid sobering problem. And we show that our algorithm can find basically the optimal solution for most problems within 1 millisecond. And the result is very robust execution of some contact-rich manipulation tasks. And you can do so without precise modeling. Like here, we explicitly show that with some modeling error, the control can still work. So we just talked about one of the failure mode. The other failure mode is the unexpected contact modes. Okay. To better illustrate the mechanism of it, let's use this very simple example where you have a square robot at hand and a square object. Okay. So let's say you're applying a one-dimensional velocity control. You try to move the hand to the right. The problem is that all the four situations I'm showing here could be feasible, depending on the exact friction and the exact geometry of the task. And more specifically, we can see this problem, we can see this ambiguity more clearly by looking at the forces that belongs to each contact mode. So this weird figure is a three-dimensional space. It represents the generalized force space of the object. And every facet of this cone here represents the set of feasible forces in one contact mode. So we need to somehow robustly select one of them as the one desired motion. So our method is, on a high level, starts with running the hybrid sobering algorithm we just mentioned, which give us some velocity controls. These velocity controls are compatible with your desired motion, but they will not be compatible with many others. So by applying those velocity controls, you basically eliminate a lot of the undesired contact modes. The remaining modes.
Could I ask a
Yeah, sure.
So the vertices are, I don't know, cases where behavior changes, I guess.
Yes.
In force states, yeah.
Yes.
And you're assuming that you have friction.
So yeah, so this is to draw this figure. I assume a certain friction just to illustrate.
Right.
Yeah, but yeah.
Because it's rigid and you have friction, we assume therefore we have convex cones is what we're going to wind up constructing.
Exactly.
In force space.
I omitted a bunch of technical detail here, but here you see the sign SLFF. That basically corresponds to contact modes of each of the 4 contact points.
Okay.
Yeah. So if you're in a contact mode with more constraints, then the force you can use is also more. So yeah. Great. So after you eliminate some of the contact modes, you can use the remaining force control portion to robustly select one mode from the others, among the others. Yeah, that's the high-level intuition of this method. And with this method, we are able to solve some pretty interesting tasks. Like on the left, we can slide an item up a stair. This is basically using one model that works for 9 different objects. On the right, like we can demonstrate some pretty delicate multi-contact manipulation skills that are even harder for human to do. So, so far I have been talking about control, basically how do we make sure things don't go wrong at one time instinct. But we might as well extend that time horizon a little bit and do planning a robust motion for a longer horizon. And to do so, we basically first identify 2 causes of failure from the method I just described. Basically, the first one is geometrical uncertainties. Basically, like the shape of the items you are interacting with is not accurate. That means your desired contact mode might not even exist. And second is just disturbance forces. So the mode exists, but you don't have the right force to stay within it. Both can be quantified and be used as metrics. So we basically have some numbers we can compute to evaluate how reliable certain mode is. And then we can use this stability margin in sampling-based planner, like for example, the typical RT-style planning, where you start with a tree in your state space. You randomly sample a state in this state space and try to find the state that is on the tree but closer to the randomly sampled point. This is a typical RT. We change the extension step. Okay, so instead of growing the newly selected node towards the newly sampled node, we grow multiple branches. We grow one branch for every feasible contact mode. And then we we compute the stability margins for the newly sampled branches and only keep the ones that are past some threshold. So this way, we essentially do sampling-based planning, but we maintain a solution with high robustness. Okay. And this method is very effective in planning multi-contact manipulation. So for motions with maybe 5 to 10 contact changes sequence, we can get a solution typically within 10 seconds, and they can be executed pretty reliably. Okay, so half-time summary. So if you are able to obtain some modeling information, like shape of your object or locations of the contact points, there are methods available to give you very robust compliant manipulation. So this type of approach has been very useful in some industrial applications that I was involved, like in logistics or in some manufacturing applications. But of course, this pipeline does not always make sense. Sometimes it's just too costly to set up the whole perception system or to obtain a useful model. In those cases, we ask ourselves the questions: can we expand on the recent progress on imitation learning and learn a compliant manipulation policy directly from human demonstrations? Because apparently, us humans are very good at this. So in the second half, I will present our recent work on adaptive compliance policy, which is a behavior cloning method to learn a compliant manipulation. So a quick overview of the method. You start with a data collection system that is able to record like a variable compliance behavior from human. Then we have a post-processing step to compute the compliance profile from this data so we can have a label. Then you can use supervised learning to train a policy that can predict not only the position, but also the compliance profile. At test time, the learned policy will predict a bunch of things. Okay? It will predict your target position, target force, and the target compliance parameters, which you can fit into a traditional compliance controller of your choice. In our case, is a admittance controller. So next, I'm going to talk about some of these modules in more detail. For data collection, we chose kinesthetic teaching, where we put a robot into a very soft mode using a customized admittance controller. So the robot has zero stiffness, a very low inertia, and a very low damping. So you can basically easily move it around and demonstrate different behavior. And with a well-designed handle, you can easily apply either force or torque to the robot. And the system will record pulse from the robot and force torque. Like we have a force sensor close to the tip of the tool to give you a clean force signal, and RGB images from wrist-mounted cameras, so we can train a visual mode policy. So the next step, once we have collected the data, is to post-process the whole data set and generate the compliance labels. Basically estimate what will be the good compliance at each time instant for every episode. However, that turns out to be a yield condition problem. Let me explain why is that. So you can typically describe compliance by a spring mass damper system. Basically, your force is, like the force you feel is generated by some inertia, some spring, and some damper. And to simplify things here, we assume the manipulation motion is not super fast. So the acceleration and the velocity are pretty small. So we can ignore those terms and only look at the spring term, which is parameterized by a stiffness matrix. That's your spring constant, and a reference position, which is at which position your spring will have no force. Okay. So let's consider a simple one-dimensional manipulation problem. You have a one-dimensional card. It has a position. It has some spring constant, and then you drive this card towards a wall. Okay, and of course the card will stop. You will record a force position profile. The question is, can you recover or estimate the spring constant here from the data we have? Unfortunately, you cannot, because either of the two situations could happen. You could have a very rigid spring, which only deforms a little bit, or you could have a very soft spring that deforms a lot. We don't know where the reference is. That's why it's ill-conditioned to compute the spring constant. So sounds like this is a mission impossible. Okay. So our solution is actually instead of attempting to precisely recover what compliance human was using, we chose to find one compliance profile that actually is very useful. It's useful enough. And our strategy is very simple. Our robot is only compliant in the direction of large force feedback. Right? So that means you look at your data set, and at any time instant, if you see a large force, that means you can set the robot to be very soft in that direction, use a low stiffness. In all other directions, you make the robot very rigid. Okay. So this is a very simple rule, but it turns out to be highly effective in two ways. First, it gives you robustness towards force disturbance in any direction. So why is that? So imagine you have some disturbance force in the direction of your feedback force. Since you have a large feedback force, that disturbance has to be even larger to cancel out your current feedback force to break the current contact. If the disturbance force is in other directions, well, you have a high stiffness control, so you naturally is resistant to the disturbance forces. So that's where the robustness comes from. Also, this method can guarantee safety under mild conditions. We can prove that with just one-dimensional compliance, you will never have a kinematic yield condition problem, or you'll never have like a huge internal force, as long as there isn't too many constraints on your robot. So this assumption in the 2-dimensional case basically means the contact constraints on your robot cannot form a sharp angle, which is pretty rare in reality anyway. And as for the magnitude of stiffness, you can basically, so for the high stiffness value, you can set it to a large value to empirically ensure good tracking. And for the low stiffness value, technically it should be 0, but we found it helpful to give you a smooth transition. So at this point, we are able to fully construct the compliance profile from human collected data. And we're ready to use it to train our policy. And as for our policy, we have a special design for the action space. So with our choice of robot compliance, we don't have to predict the full force vector and the full stiffness matrix. We can encode all the information we want in this 19-dimensional vector per robot arm. So it basically has a reference pose and a virtual target pose, which I will explain in a bit, and one value for the stiffness. So this virtual target is where the robot attempts to reach. It basically explains your desired force as spring force. Okay, so let me give you some examples. So this formulation actually makes it very intuitive to realize and for debug your policy. So in this figure, the yellow dots are the reference pose, the orange dots are the virtual target. When these two are different, their difference shows where the robot is attempting to apply force. And this way, since the force stiffness matrix is being reconstructed from a very minimal representation, we don't need to worry about the positive definiteness of it. So as you may have known, the stiffness matrix has to be positive definite. So if you use a network to predict all entry of it, you have to somehow enforce that constraint. Here we don't need to enforce this constraint. So here are some evaluation results. So with our method, like in this with wiping example, our method is able to pretty reliably carry out the wiping motion. We compare the method with two baselines that use constant compliance profile. One is a high compliance policy, another is a very stiff policy, which are very typical choice in other robotics work. Comparing with the compliant policy, our method is able to ensure precise motion even under wide restriction. Let me play this again. So the baseline compliant policy, the motion can deform a lot because of the friction on the waist. And the baseline stiff policy can easily create a huge internal force, and like we repeatedly break the robot tool. Here's another example where we use a rubber hammer to hit the item that provide force disturbances. Our method is basically not affected because we have robustness against force in all directions, whereas the baseline compliant policy quickly go out of distribution. This is another example where the robot is attempting to flip up an item against a corner. So our method is able to pretty much achieve the task 100%, even with unseen items. The baseline compliant policy often fails the task because the motion gets affected by force noise quite frequently. This is the stiff policy baseline, where it's easy to have catastrophic result when there is like positional uncertainties. Cool. So I talk about a lot of technical stuff. The take-home message I hope to convey today is actually very simple. So you don't need to remember any equations or weird figures that I mentioned, but I want you to know that first, active compliance is very useful to provide both robustness and accuracy to manipulation if you can find a right one. And with pretty with pretty simple modeling information, you can actually compute the optimal compliance profile very efficiently. And if you don't want to do that, like if there is no contact information, then the adaptive compliance policy we presented is a good way to help you obtain a compliance policy that is robust directly from human demonstration. Yeah, that's the last of my technical slide. And I will say thank you to my collaborator, and I'll keep this page and take questions.
Thanks so much.
Oh, here's a question. Yeah, here's one.
How often do you need to stabilize the compliance direction? How often do you need to do that?
So in the model-based approach, that's a decision made by yourself. So the algorithm computation is very efficient. You can compute, you can update direction up to like 1,000 hertz if your computation permits. But in practice, like 5 hertz is sufficient. You don't need to change the compliance profile very often, because a suitable profile can last for quite a while. It can endure the uncertainties and changes that come with a slow update. For the ACP, we update the policy. So we update the policy every maybe 2 seconds, but every time it predicts a trajectory of about 3 seconds into the future. And that 3-second trajectory is parameterized by maybe 16 or 32 points. Each point represents a certain compliance profile.
One more. All right. Well, then, yeah. All right.
Thank you.